So today is our seventh class. So let me get on with a quick revision of the previous class. As per the previous class, we've discussed briefly about decision trees and Gini indices. So can someone briefly go about that? What do you understand by this?
That there are two node kinds of nodes, pure
Mm-hmm.
nodes and impure nodes.
Mm-hmm.
So whenever there is a only one category, yes or no, then that nodes are pure nodes. And when there are nodes under S as well as no category, then there is impure nodes which can be further again bifurcated. And then again we are going to consider the Gini index of the other category, and whichever is lesser, we are going to put it on the top. And likewise, we are going to refer to that kind of feature, and we are going to arrange all these things in hierarchical manner.
Right, right. So this hierarchy of how we are going to choose what is our root node and what is our decision making node, and then finally what is our leaf node. So this entire algorithm that we prepared, this entire hierarchy that we prepared on the basis of binary yes and no classification at each point, that is called as decision tree. So I hope this concept of decision tree is clear. You cannot have triplets here. You cannot have quadruple points here. It is supposed to be binary. It is either yes or no. So you have to make your statements. You have to make your questions such that it is essentially classified in the form of yes and no statements. Okay, and at every yes and no combination you can add or input another feature vector for the classification, and that could further bifurcate your impure nodes if at all. But essentially the idea is that you get on with it, and your leaf node should be able to give a clear cut decision on whether it is finally a yes or a no. So I hope this part is clear. There is no doubt in this, right?
It is clear.
Okay. Okay. So moving on, we will move towards another aspect, which is about information gain. So here is a Cartesian plane. I hope you are able to see the points clearly, the blue and purple points.
Yes.
Okay, so these are some data sets that are given, and on the basis of this data, now you have to train your model, and on the basis of the training of your model, any random point can be given to you, and you may be asked to predict whether it will fall in this blue category or whether it will fall in this purple category. So, if this question statement, this problem statement is clear to you, can you give me a clear-cut earmarking of any zone that would distinguish your blue points with purple points? Just one line or one curve, anything?
Circle.
Yes, it can be a circle. But what about a line? Is there just one demarcating line that you can draw?
No.
Not really, right? So we will work with lines, and we will see how we can classify this such that you can, very quickly arrive at a conclusion. Okay, so with this, we come to the concept of uh, decision tree classification. This is the second approach that we are taking, and we will not be using Gini impurities for computing these value at the nodes, the features that we choose. So, okay, this is your vertical axis. We will label this as x1, and this is your horizontal axis. This we will label as x0. This nomenclature is clear?
Yeah.
Okay, yeah. Let us take this example. So suppose we draw a line like this at x1 less than or equal to 4. Okay, so at this point, at this line, anything which lies below this will be counted in yes, and by default, which one is the yes side?
Left side.
Left side. And which one is the no side? The right side. Okay, so if this condition that I am stating here is satisfied, then the point falls in this zone. If this condition is not satisfied, then it's a no and it falls in this zone. In totality, I have this many purple points and I have this many blue points. Okay, so if I count it, then it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 purple points and I have 10 blue points. all are equal, right? So here I have this total population. Now on the basis of this condition that I have provided here, I am classifying whether it is a yes or a no, and I see that these many points fall in the category of yes, and these many points fall in the category of no. I hope this figure is clear.
And why did you select this condition less
It's
than?
random.
Right.
It's random. It's just for illustration. There will be hundreds of such conditions that you can choose, and you can run the loop for different conditions and see which one is giving you the best information gain. It works similar to the condition of Gini impurity, provided your algorithm should be able to read it.
Even the color choice is random. You've selected left side is purple. Even that is random. You can even select the blue one, right? Choice of color is
No. See, there are two aspects here. One is the magnitude, the value of x1 and x0, and the second one is your color. Okay, so essentially, color is binary, which is blue or violet or purple, whatever you call it. This or this.
okay.
So this binary classification of this color, either this or this, is our output that we have to predict, and our input is in the terms of values where it is located on the Cartesian plane. Since a
Okay.
Cartesian plane is 2D, we have two values in terms of the horizontal axis x0 and in terms of vertical axis, that is x1. So now, preliminary basis, we are assuming that this is our demarcating line. So anything which falls below or equal to this line, everything here, we count it under this left side, which
Okay.
means yes. And anything which falls above this line, we count it here on this right side. And that too, we are segregating on the basis of color, so it is clearly visible how many counts are there. In totality, if you add this and this, it should result into this because this is the total population.
Agreed. Fine.
Okay, so now that you are able to read this
Ma'am,
figure it.
sorry.
Yes.
Why only horizontal axis, ma'am? Can I take vertical as well?
Yes, sure, you can. Essentially, you have to build a classifier, a tree, a model. You have to train a model. There can be thousands of correct model. Essentially, they should be able to give correct predictions. That is what you're trying to do. You could assume a vertical line, you could assume a horizontal line, a slant line, you could even have parabola, or you could even have a circle, anything, any classifier that could give you a decision. Anything is fine. Any model which works is fine. But here, just for the sake of simplicity and understanding, I am starting elementary. This is completely arbitrary. If this is
Okay.
the condition, then we will compute what is the value of the entropy and information gain. And accordingly, we will choose another classifier, maybe some other line, and see if that works. And if that works better, then that should be chosen. And this is taken in the form of an iteration, and the code is run such that you get the best classification.
Yes.
Okay.
Yes.
Okay, so if that is clear, then we move ahead and we see that, okay, how many points are purple here? In this yes
Eight,
side,
eight,
Eight.
eight.
8
8.
are purple and 2 are
No,
on this
left
no
side,
side.
right side.
Okay, and similarly here, blue,
Points.
6.
6.
6 are blue here in this yes side, and 4 are blue
On
here
the
on this
on
right
the no
side.
side.
If this is my condition, provided this is my condition, this is the classification that I get. So here, do I get any of the pure nodes? Any of these
No,
can be leaf
no,
nodes? No,
no.
because on both the sides I have both colors, blue as well as purple. So none of them are pure. It has a mix and match of both sides. Majority may vary, but it has a mix and match. So if that is the case, then what about this? If I choose another classifier, say x0 less than minus 12, say this vertical line, then I get this classification. Again, this is completely random. It's arbitrary. If I choose this classification, however, then I can see that there is a pure classification at this side. This is decisive. This is impure, of course, but this is pure. So which one do you think is better?
Obviously, the second one will be better.
Second one is better than the first one. I'm not speaking in terms of absolute terms, I am speaking in terms of relative terms. Provided I have to choose amongst the first condition and the second condition, I would prefer to go for the second condition. Why? Because I am getting a pure decision here, pure node here. So I'll be able to give a decision better here. So far, so good? Understandable?
Yes.
Okay, so this was
Yes.
qualitative. Now, in terms of quantity, we will discuss these two conditions. See, our focus is on these two conditions, but conditions can be many. It can be many, it can be varied, but we will focus on these two such that we can understand the mathematical aspect associated with it. So now that you know this, yeah. So, what is the information gain associated with this second condition? Because the second condition is more decisive. Qualitatively, we've been able to assess that this second condition over here, x0 less than equal to minus 12, is a better classifier compared to x1 less than equal to 4. So, we will now compute what is the information gain associated with it. So for information gain, we need to know what is the entropy associated with each of it. So for the root node, if I have to compute the entropy for this first one, what will it be? Probability of I, here this I is purple and the second I is blue. So for the blue case, if I have to compute the probability, then it is 10 out of 20 points. The total population is 20, out of which 10 are purple. So it's 0.5, right? So if I substitute pi equal to 0.5, then what do I get as the entropy for this? Minus of 0.5 times log of 0.5.
Ma'am, please repeat.
Okay. Which part? This entropy part, right?
Yes, ma'am.
Okay. So, in order to compute this information gain, you need to find out the entropy associated for each of the class or classification. So, starting from the root node to the leaf nodes or the intermediate nodes, we will be calculating the probability associated with it, and on the basis of the probability associated with it, we will compute the entropy associated with it. So, the entropy has this designated formula, right? It is the summation of the probabilities of all the cases. So it is the binary case. So there will be two summation terms here. Basically, if you expand this summation, there will be two terms here in the expansion. So here you will get one term for this purple dots and another term for these blue dots. So for these purple dots, if I count the population for the root node, then I find that I've got
10.
10
10.
dots.
10 purple dots out of how many total dots?
20.
20. So 10 out of 20 is 0.5.
0.5 probably.
Right. So if my probability is 0.5, then for these purple dots, I get minus of 0.5 times log of 0.5. Now this summation I expanded, so there is another plus term, and then again for the blue dots, I get again minus of 0.5 times log of 0.5.
Yes.
Okay.
Yes,
So
ma'am.
so now that this part is clear, so basically I am going to compute this. So I will be getting a total calculation of this, right?
Yes.
This is the entropy for this set, this root node.
For purple and for blue.
Yes, for purple and blue. Our classification is purple and blue, so it has to be. Or binary, if you want to assume, you can say purple is yes and blue is no. Okay, or 0 and 1. It's binary.
Yes.
So far, so good.
Yeah.
Excuse
So,
me, ma'am.
yes,
Is the base of the log 10 or is
no.
it?
Here, the log base is 2. We are dealing with a binary classification and the log base is 2. It is not 10, mind you.
For any classification, the base is 2 only, no?
No.
For
For
calculating
binary
entropy.
classification, the base is 2.
For non-binary classification, the log base will be other thing.
the log base will change according to what is your classification. So if you have multiple terms, say suppose you have to take the probability for 3 terms, this summation will expand not to 2 terms, then it will expand to 3 terms.
Okay, then
Although
log base will be
3 in that case. However, in decision trees, it is irrelevant because essentially decision trees means that it will be binary. It has to be.
binary.
Yes.
Okay.
So now from this formula, we can compute the entropy associated with this. Now similarly, we can compute the entropy associated with this set as well, right? Which was our first condition, x1 less than equal to 4. We have this and this. So for these two sets, it is possible to compute the entropy. How would you compute it? What is the total population here?
That
8
is
plus
8 plus 6.
6. So
14.
total population is 14.
14.
And out of it, how many are purple?
8 by 14 is the probability.
Yes, 8 by 14 is your probability. So 8 by 14 is your probability here, and you put your probability value here to compute the entropy for the first case. Similarly, second case,
6 by 14.
6 by 14, and you compute the entropy for the second case, and you take a summation of that, and the summation of that will give you the entropy for this set, and that gives you 0.99. What about this?
6
2 by 6,
2 by
2 by
6.
6 and 4 by 6.
2 by 6
Right.
and 4 by 6.
4 by
4 by
6.
6.
Right? And that will give you the entropy for this case.
Okay.
What about this?
4.
This
4 by 4. 1.
1.
probability
4 by
1.
4 is 1, and 0 by 4 is
0.
0. Okay, and if you compute the entropy, what do you think is the value of entropy?
1.
Minus 1.
0,
Log
0.
1, 0.
Exactly. It's 0. And similarly for this, 10 by
Again.
16
10
6.
by 16.
Yeah.
10 by 16.
and 6
10
by
by
6
16.
by 16.
6 by
Right?
16.
And that will give you the entropy here. Mind you, again a heads up, your entropy is calculated with a logarithm of base 2. So for the first case, when it was 0.5 times log of 0.5 plus 0.5 times log of 0.5, you should remember that that 0.5 is taken as a log of base 2. So it comes out to be 1.
Yes, yes.
So if that is the case, then this is the entropy that you get in all of the cases. So if the entropy for the root node and the leaves are computed, then the information gain is calculated from the entropy of the parent minus summation of the weighted average of the entropy of the child nodes. So this is your child node 1 and this is your child node 2 for the first condition. So for the first condition, your entropy of the parent is 1. So you take 1 minus, what is the summation of this? See, the weight of this population is
14. 14.
14. Out of what is the total population?
20.
20. So 14 out of 20 is the weight of this set. And accordingly, 6 out of 20 is the weight of this set. So if you take the weights and multiply it with its entropy value, add it, and this summation, you subtract it from the parent node entropy. In this case, 1. Then what you get is information gain. Clear so far? Is this formula understandable, what we did here?
Yeah.
The first IG1 we got for the right side, no? Sorry, left side, and IG2 we got for right side.
No. IG1 is for the first condition, that is x1 less than equal to 4,
Yes.
which is this case. This is one classification and this is your second classification. The
Okay, so
first
based on
classification is based on your first condition, which is x1 less than equal to 4, and second classification is based on second condition, which is x0 less than equal to minus 12. And we are comparing which one is a better classification condition amongst these two. In order to compute that, we are using the formula for information gain such that we can compute which is a better classifier. See, On a preliminary basis, you told me that the second condition seems to be better because it gives one pure node at least. So one node is leaf and decisive. Whereas in this case, the first case, even one node is not a pure node. So on a qualitative basis, you told me that yes, the second classifier is better. X0 less than equal to minus 12 is a better decision maker as compared to X1 less than equal to 4. But now I'm saying we need to do this quantitatively. Because we are not doing this manually, we have to use an algorithm. So we have to put some value associated with it so that the optimization can be done. And that value is done firstly. In the previous class, we had discussed Gini impurities. Now we are discussing information gain. So in order to compute the information gain, you need to have the idea of the entropy of the parent node and the entropy of the child nodes. So in the first classification condition, we had these two child nodes. In the second classification condition, we have these two child nodes. So for the first condition, we have computed IG1, which came about to be 0.034. And in the second condition, we have computed IG2, which came about to be 0.24.
Yes, ma'am. Yes.
Okay, so now that we've understood this formula, clearly which case shows you a better information gain?
IG2.
Second case.
IG2. So IG2 information gain is higher. Therefore, we will choose this classifier as compared to this classifier. Now, what if I could, give a range to my computer, my algorithm, and say you vary your x0 from here to here. And wherever you find the maximum information gain, you take that. So I can run a loop something like this, right?
Suppose if we set x naught less than or equal to minus 10, then also the same information we get.
Yes, of course. That is what I'm saying. You will get a range here because your data set is less. But assume that you have a very complex set of data. This is just for the sake of illustration. This is a very simple and very less amount of data. This much data is not very comprehensive to compute or predict with very high accuracy that color will fall in which category. But then,
by using iterations only, we have to select this threshold value.
yes, so you can use those iterations to segregate and maybe choose classifiers which could give you the highest information gain. It's possible, right?
Okay, thank you.
Perfect.
So you will be able to use these concepts in order to calculate what is the best classification condition and how you build your decision trees for a specific data. So, for example, here is an illustration of that. See, the first condition is x0 less than equal to minus 12. We selected it from these two conditions. Okay. So, if these two conditions are taken, then the second one works better, and we took that. So, we came about to one pure node which cannot be further classified, and another impure node which can further be classified. So, for further classification, we chose another condition that x0 less than equal to 9, and that further gave another pure node and another impure node, and that impure node again we imposed another condition, and now we are left with two pure nodes which cannot be further classified. So now this is a full built trained decision tree, and any value in anywhere in this entire Cartesian plane, if I put my point, it can follow this and it can give a clear cut decision whether it is a blue dot or a purple dot. According to this decision tree, anything which falls in this zone will be purple. Anything apart from this zone will be blue. That is how this has been treated.
Ma'am, in this example, we were seeing the class values to be quantitative. We knew the values of green, the number of green dots, and the number of purple dots. This can be applied on a qualitative classification too, right? For example, in the last examples, we were able to see. We had an example where we have numerical values.
Age.
A.
Right.
So this can be applied there, or is this applied only for
It can
class?
of course be applied there, but in that case you need to make your condition such that it gives binary outputs. If it is a figurative expression, if it is a number, if it's a numerical value, then it has to be modified such that now it is a classification statement, binary, if
Okay.
or statement. Then only you can use it. Directly you cannot use it. So maybe you could use a condition for that number and say that if it is less than this, then it is a yes. If it is more than this, then it is a no. Or something which can classify it.
Okay.
For
So this
example,
is
in the previous case, the example that you are discussing, we had discussed simple averaging of all the numbers in the data set, and we use those numbers, those average numbers, as the classifiers if it is less than that or more than that. So now it became an if and or condition statement, and now that conditional statement can be used as a classifier, a binary classifier.
okay.
How you came to the base fit, like x1 is less than equal to 9? You have taken this condition, but this is again a trial and error, no?
Yes, this is
At the
completely a trial and error for the sake of illustration. But this trial and error can be, mechanized, or I would say automated. If you use an algorithm and feed a range that okay, from this range to this range, I want this to be done. For example, I can see that all my data sets are constricted from this range to this range. So if I feed an algorithm with a loop of taking the x0 values from here to here, then it is possible that it will give me 1 or 2 points or whatever number of points with the highest value of information gain. So that is possible to get.
by which mechanism you will get?
So if you build an algorithm such that you impose a condition that, say, suppose you have a variable, say ig is my information gain variable. Okay, so I compute the value of ig for, say, the first line. Say suppose this is my first boundary, some arbitrary value of x0. This is my first boundary, this is my last boundary. So I fix a range that you iterate from this value to this value in, say, a step size of 1, or maybe step size of zero point 0.1. And from all those iterations, you compute what is the information gain associated with it. Okay, so from that, if it gives me the information gain, now I say that if the new information gain is higher than the previous one, then you substitute the previous one with the higher one. If it is not the condition, then you keep the information gain as the previous one, and this loop goes on till recursion happens from here to this last boundary here. So essentially, when I run this loop, wherever my information gain is the maximum, the highest, it will return me that value.
Madam,
But
this
you will get the maximum information gain only at the end of the loop.
Yes, of course. It has to run the whole iteration. The comparison needs to happen from the start to the end. And wherever I get the maximum information gain, I choose that point. That could be here, that could be here, that could be here, that could be anywhere. But yes, at the end of the loop, you will be able to get that.
Clear.
Madam, one doubt.
Yes, please.
This evaluation of finding out the best classification is by running it across a range is only required at the root node, and from the rest of the leaf nodes, you can identify that if you can evaluate the classifier which can find pure and the pure classification, you're done. You did not do the computation.
Could you elaborate more?
We are doing this computation only for the root node. We have to run this logic only for the root node classification. For the rest of the leaves, do we really need to run this classification? Because we can identify the impure classification, we are done.
Not really. No, that is not the case. It is not just for the root node. Wherever you get a bifurcation, whether it is root node or intermediate node, wherever you are putting a condition, you need to run this. See, your root node essentially is, of course, having this condition, but any impure node will also have some condition. Although leaves will be giving a final decision. So here we do not need further bifurcation. We do not need further if but any statement, right? So here this is a clear cut demarcation that if it falls in this category, this will be blue. So here I do not need further bifurcation or imposing any condition. But however, in this case, that is not the scenario. Here we do need bifurcation. We do need another if or statement. So here there will be another condition. And to put that condition, again you can run another iteration, which of course falls in the boundary of this,
Okay.
right? This
Right.
this side is no for this condition. So that means your boundary is restricted to x0 greater than 12. It cannot evade that. If it is evading that, then this is falling here. So this
Okay.
condition has to be satisfied for all the nodes beneath it,
Okay.
right? So if it is on the right side of this condition, then that means you have to satisfy x0 greater than minus 12 always, all of these nodes.
Soumya ma'am,
Yes.
ma'am, is it necessary to run the loop for x0 as well as for x1 minimum and maximum value to decide this
No,
kind
it's
of
not
condition?
necessary. It depends on your data. Everything depends on your data.
At the second level, you selected x1. How you
Yes,
come to
you
know
could-
that x1 will be the best condition to bifurcate this?
You could run it for x0 as well as x1. But from the pictorial graph, you can very well see that only on the basis of x0, it's very difficult to demarcate. You will have at least one point of another color line, only on the basis of vertical lines, or only on the basis of horizontal lines. It is just not
It
possible.
it means we have to check on x0 as well as x1.
Yes. But however, there may be data sets where only vertical lines may be able to capture the integrity of the whole model. It doesn't need to always have horizontal lines all the time, or the opposite scenario may also occur. Say suppose you get a region where say all these points here are purple, and all these points here are blue, and all these points here are blue. So then only horizontal lines will be able to demarcate that, right? But if your data set is diverse, it is mixed, which is essentially the case most of the time, then only set of horizontal lines or only set of vertical lines are not going to serve the purpose.
Okay, madam, here we are getting three conditions. No? So can we combine these three conditions to get classification in one step?
Well, it makes it more complex. Of course, you could, if it is less than minus 12, then it has to be, less than
So
minus.
the statement, suppose if I make a statement like this, if x0 is greater than or equal to minus 12 and less than or equal to 9 and x1 less than or equal to 9.
That is what I'm saying. If you club those statements, so basically clubbing those statements essentially expands to this classifier. You are just making it more complicated to evaluate. Break it down, then it is essentially this.
Okay. This all we do during training.
Yes, this is all done during training.
Once the training is completed,
Yes, so you can test a
then
data.
can we, by making a single statement like this, by combining all the conditions, can we do it?
Yes,
or
that is
not?
the whole idea behind it.
Okay, okay.
These are nested if and or statements, basically, which gives you a clear-cut distinction of what is your output.
Madam, which one is better, splitting the decision tree using the gene index or splitting the decision tree using this entropy way?
It's a very abstract question. Actually, many people favor this. Another set of people tend to agree more on this. So, it is both are fine actually. Both are used and both are very much in vogue, very much practiced, and you could work with either.
This one
Sometimes
is
it may be good for regression, sometimes it may be good for classification.
Regression, we do not use this. It is essentially meant for binary classification. In classification, also binary classification. These two things
It is
that we are
good for
discussing.
binary classification.
Yes.
splitting of decision trees using entropy has more computations. That is the disadvantage. You have to have the best classification.
No, not really. Entropy is very straightforward.
No, I mean you will have to calculate the best classification across a range. So that involves a bit of more computations.
Yeah. Either your efficiency is higher or your time is higher. So there is a balance of both.
Okay, ma'am. So far, so good.
Okay, so if that is clear, then yeah, what is the problem with decision trees?
In one of the sessions, Madam shared that decision trees gives us the classification of the data point, but it doesn't tell us what is the confidence of that classification, like in terms of probability, how much is that correct or how much is that incorrect.
Okay,
Probably.
yes. I hope you remember the concept of bias and variance, right? About training set and testing set.
Yes.
So if that is the case, then whatever we are doing here is using the training set. And using the training set, we built a decision tree. Now, the moment we use a testing set and there are more data which are different from the existing data, this may be rendered invalid. It is very much possible. This classification may not work fine on a varied variety of data. It is although
Problem,
suitable for a given data on which you have trained, but it may not be true in the time of testing. So your variance may increase.
problem of underfitting.
Exactly.
But ma'am, then why is in first place then decision tree being used if it is not going to help us on unknown data?
That is why there is a popularity of another model. Although initially this was used, and this also works well with most elementary form of data, but with complex data, many a times it does not work, and people have better models or better algorithms which deal in probabilistic terms and are better in terms of giving you a clear-cut decision. For example, I have a data set like this, and for this data set I have this point id and all the feature vectors. For example, I have 5 feature vectors here: x0, x1, x2, x3, and x4. I have my output vector y, which is binary 0 or 1. So then, using these feature vectors, you could build a decision tree which could work well for this data set. But the moment you alter the data set, for example, you change this data set, only these two points. Now your decision tree is this. So basically, decision trees are quite sensitive to the changes in your training data set. And that essentially results in a very high variance, because the moment your training data set is changed, that is, testing set comes into picture, your error may increase, and the classification may not work as fine. Then you need to change your decision trees. So for that purpose, another algorithm came into being, and this is more popular in terms of prediction. That is random forest algorithm. So random forest algorithm is based on principles of probability. Here, what you use is bootstrapped data. Now, what is bootstrapping? Anyone?
No idea,
Bagging.
ma'am.
I
Sorry,
mean,
Yeah, no idea, ma'am.
bootstrapping is starting something like in system we say bootstrap the system.
starting what?
The kernel, I mean program which is there in the kernel of the memory.
He's talking about the irrelevant term here. That is different bootstrap. This is different.
Yes,
So
Okay,
bootstrap,
okay.
I also understand that Madam shared about in bagging while explaining bagging concept.
yes, bagging is associated with it. In this context, you can relate it to sampling essentially. So, and that too, not just random picked up sampling. So essentially, repetition is also possible. For example, you have a bag full of red balls and blue balls. Say, suppose there are two ways to choose random balls from there. What you can do is you pick one ball arbitrarily and place it somewhere. Second ball, you choose from the remaining set and place it somewhere. This could go on. Or else, either way, what you can do is you could choose one ball from it, record the output, and put it back into the bag. And again, from the whole population, you choose a random ball. So these two are not same. I hope you understand the difference.
Understood the difference, ma'am. But what is bootstrap data again?
Yes. So here, either of the scenarios can be operative, and you have to state that what you are doing. And here, in this case, it is a repetition. So bootstrapping means you are essentially picking and choosing any of these IDs. You have given allocated IDs associated with each data set. So you have these feature vectors, and for these feature vectors, you have the output. Similarly, the values of these feature vectors are changed, and you have this output, and so on and so forth. So you have a whole data set associated with it, all the features that you have taken into consideration, and you have the output associated with it. So all of these set of feature vectors, you are now marking an ID associated with it. And now randomly you are choosing those IDs such that they can create sets of the whole population again and again. From this population, you are keeping the same size as the population, but now you are sampling the data. It is not the same data anymore. And you will not be using these to train your decision trees. You will be using these sampled data for building decision trees. And not just that, you have to do feature selection as well. Researchers have found that normally close to the under root of the value of total feature vector gives you the best prediction. So if say suppose 5 feature vectors are there, then under root of 5 is close to 2. So maybe 2 feature vectors will be better feature selection. So arbitrarily you could choose x0 x1 x0 x2 x0 x3 x0 x4 x1 x2 x1 x3, all those combinations which are possible. So how many feature selection combinations are possible? 5C2.
Yes, 32 combinations. No?
Right. So 32 combinations of feature selections are possible. And similarly, you can arbitrarily choose sets. For example, here there are 6 data sets. So I build a column of 6, and in this column I pick and choose randomly, repeatedly from the same set as many IDs that I can choose. For example, here 2 has been selected twice randomly, 0 has been selected once, 5 has been selected twice, 4 has been selected once, 3 has been not selected, 1 has not been selected. Similarly, another ID set has been created, training data set, on the basis of this actual data set, and here we have another set, and so on and so forth. You can go on building such IDs. From a given data set, you can build so many data sets by arbitrarily choosing this. So now you don't just have one data set, you actually have so many data sets to select and make decision trees corresponding to those data sets on the basis of those arbitrary features that you've selected. Now it's not as complex, and you can build decision trees. And from those decision trees, essentially, you get the outcome, right? And from those outcomes, you choose that outcome which is in majority, and you give a vote to that. It is basically a polling system. So, for example, if I have say thousands of such bootstrap data sets, and from those thousands data sets, I get majority as 1, y value, I get majority as 1, then what is the outcome that is most probable that I get? 1. So, this is the whole idea behind it, majority voting. So, you have bootstrap data and you do feature selection, and from those feature selections you basically use an aggregation of the model and you choose the prediction. And this totality of bootstrapping and aggregating is termed as bagging. So for example, consider an instance here. This is an arbitrary data that has been given to you, which is not a part of your population. So this is your testing data that has been given. Now, this testing data, for example, x0 and x1 has been used in the first case. So let us use this decision tree. So from this decision tree, using x0 and x1, my x0 is 2.8 and x1 is 6.2. So if I put it, then what is my outcome? X1 6.2 is no category. Yeah. So my outcome is 1.
1.
1. Okay. Now moving on to the second one. Second decision tree of the bootstrap data. X2 and X3 has been used here. And my root node condition is X3 less than equal to 4.6. So my X3 is 5.3 and it is not less than 4.6. So what does it become?
0.
0.
0.
Right.
Right. So my answer is 0. Now what about this? It is trained on the basis of x2 and x4. So my root node condition is x2 less than equal to 4.1. My x2 is 4.3. Is it less than 4.1?
No, ma'am. No.
Okay. So
4.3
it
is
goes
not
to the right one. Now x2 less than equal to 4.6. Does it satisfy?
4.7. Yes.
Yes, it does. So it goes here. What is my outcome?
1.
1. So yeah, this is my decision tree. It gives 1. Now x1 and x3. So x1 is 6.2 and x3 is 5.3. Yeah. So my condition is x1 less than equal to 4.4. So does it satisfy?
No,
No. So it moves
because it
here.
is
Now x1 less than equal to 6.1. Does it satisfy?
no
No. So what is the outcome?
1.
1. So I get 1. So out of all the decision trees, what is the majority prediction that you get here?
1.
Considering that 4 is the number of decision trees that you have, the
1.
prediction is 1.
1.
So you take that prediction and that is your outcome.
Okay.
The moment there is a doubt here, say suppose 50-50, here also 0, here also 0, here 1, here 1. So in that case, the data is not sufficient or the model is not trained enough to give a clear-cut decision for the given data set.
To we have to take all the combinations, or some combinations are sufficient.
uh, you could take as many combinations. The moment you increase the number of bootstrap data, it is going to further improve your prediction. For
Classification.
example,
Yes.
I could elaborate this with an instance. Say suppose you have a coin and you flip it say 10 times and you count how many times you get heads and how many counts you get for tails. So if you flip it 100 times, maybe that will enhance your confidence of prediction. That okay,
Yes.
yeah.
Definitely.
So if you do it
Definitely.
10,000 times, it is further going to enhance that. So it's all
Yes.
about trials. It's all about how much of improvement you can do for a better prediction capability.
For this case, we have 32 possibilities here.
32 for
Suppose
feature selection.
for
Bootstrapping,
features,
so many possibilities.
5C2, we are doing
5C2 is for feature selection.
feature
See,
selection.
feature selection is one part. This is
Hmm.
you are selecting 2 out of the 5, right?
Okay, we can also select 3 features.
Yes, you could, but it has
But
been found that accuracy has been better in the case of close to the under root value of total number of features.
n,
So
if
yeah,
n number of features are there, root n is the best
way to go about it.
select the
Yes,
number of features.
yes.
Suppose
So
if we take here x0 x1 is one combination, x0 x2 also another combination.
right,
Like that, if you take all combinations that are possible for these 5 feature sets, can we get 100% accurate classification?
that's just not possible.
Okay.
100% is not called probability. 100% is called certainty.
Okay. Okay.
Okay, ma'am, I didn't get you. What is this 2.8, 6.2, 4.3, 5.3,
Okay,
5.5?
so these
Test
are your
data.
feature vectors, right?
Test
X1,
data.
x0, x1, x2, x3, x4, and y is your output, right? So if you have trial data, say suppose 6 data are given to you here, and you have different values for all of these features, and you are getting the value of your y. Similarly, you have different values of all of these features. Again, what is the value of y? And this goes on till your whole population of your data set. Now, you have been given an arbitrary data set which is not a part of your training data. This is a testing data. And now you are running this testing data through your algorithm to see what is your value of y, whether it is 0 or 1.
Okay,
This is your testing data. The value of these feature vectors are not a part of your training set. This is a new data. And
okay,
from
ma'am,
this
got it.
new data, you are predicting whether it is a 0 or a 1. So one way to go
Ma'am,
about it is a complicated way, that is decision tree. Another way is simplify it, use those decision trees, but not for so many at a go. You use it for simple ones and you make it random and you make a forest of that. You train a forest of that. So I hope you can relate the connotation of these words, random forest.
ma'am, in layman terms, can we say that bootstrap data is a subset of the training set data?
Yes, of course. Yes, of course. With repetition. It is possible that repetition of data is allowed, or it is also possible that repetition of data is not allowed.
Okay, ma'am, you discussed two cases. in first case we are taking randomly the one ball from the bag and then we are putting it aside. And second case you said that you are putting it back into the bag and again selecting the randomly, right?
Right. So
So
in
how these
that
two
case,
conditions?
if you operate with the first case where you are putting it back and then you are taking out another from the whole set, where you are not having any decrement in the population, then it is possible to maintain the same size of the population and still have variety of data. However, in the second case, if you maintain the same size as the population, then essentially it is a repetition of your first set. These ID may change, but the whole training set will remain the same because your size of population is same, right? Say suppose my population size is 6 here, and I keep my bootstrap data set size also 6, and I'm also not putting back the balls. So then I will take out 6 times, and eventually my whole ID will undergo a permutation. That's all. The combination remains the same. The order may vary, but essentially the combination of the whole data set will remain the same because I'm not putting back the balls. So if I'm to adopt the second approach, then the size of my bootstrap data should change. You are supposed to make a new data set out of this existing data set for
I mean to
training.
say that there will not be any repetition of the IDs then.
If there is no repetition of the IDs, then the size of the population should vary in order to create a new data set. Say suppose this is one data set, right? 0, 1, 2, 3, 4, 5. For the sake of simplicity, this allied matrix you forget. Okay, so this is your data set 0, 1, 2, 3, 4, 5. Now, from this 0, 1, 2, 3, 4, 5, if you were to generate so many columns, combinations, one way is to allow repetition and keep the same size. Another way is do not allow repetition but change the size. If you do not allow repetition and keep the same size, then essentially you will generate this whole matrix only with a permutation. That's all. The numbers order will change, but the combination will remain the same. Say suppose I pick 0 out of here and I have kept it aside. I'm not putting back this 0 again. Right? Now I'm left with 1, 2, 3, 4, 5. So now from here I pick 2. Now I have not kept 0 and 2 inside. I'm left with 1, 3, 4, 5. Now from there I choose 4 and I have not kept it inside. And now I'm left with 1, 3 and 5. And I repeat this. Essentially what am I getting? I'm getting 0, 2, 4, 1, 3, 5. So there is just a permutation. That's all. The order has changed. But
Okay.
essentially I'm left with the same data. It is not a new data set. It is the same data set.
Right. But ma'am, this x0, x1 or x0, x2 or these combination may vary, no? Then.
This feature vector and the output label associated with it is allied to this tag 0. So when I'm referring to the tag 0, it comes with this whole set. This is my data, one data, where your input is these 5 and output is this 0. So your input and output combination is one data. You are designating it as some ID, maybe some number or maybe some alphabet or anything which you want to designate. Maybe A, B, C, D, E, whatever. This ID is not a value. This ID is just a tag to label one data. This whole thing is one data. This whole thing is another data. Assume that, for the sake of simplicity, it is just one X and one Y. Then what would it be? X is your input, Y is your output. Now here in place of X, you have 5X, 5 features to use for the prediction. But it is essentially one data. For example, if you were to compute the price of a house, then the price of a house, the value of the price is your Y. And the variables associated with it, the number of bedrooms, say suppose x0, the number of years, say suppose x1, say the number of floors, x2, the size of the square feet, x3. So all these features associated with it are different feature vectors. But essentially the combination of all the features, value and the output price is one whole data set. You cannot treat it separately. Now you may designate it as, say, suppose A. This is my ID A, which has this data set. My ID B, this is this data set. My ID C, this is this data set. So when I say A, I'm referring to the first data set. When I say B, I'm referring to the second data set. Or else, instead of ABC, you could use numeric IDs 0, 1, 2, 3, 4. These are not numbers. These are ID that you are designating. Serial numbers, you could say. But if you do not allow repetition and you keep the same size for the bootstrap dataset, then essentially you are repeating this population. So training on this population and training on that population is not different. It is the same. But if you change this dataset, if you pick and choose randomly from this dataset, although the size is same but repetition is allowed, then you could get a different dataset from this whole dataset, which is a subset of this, allowing repetition as well. Now training on this and this is not same. And training on this and this is not same. Training on this and this is not same. It is different.
Yes, ma'am, I got it. Thank you.
Can you please explain once x0 x1 column is there na ID 202455, how you got 2 or 0? Just please repeat.
I didn't get to there. I took a set of, say, suppose this is my bucket, and in my bucket I have these IDs, and all of these IDs represent these data sets. So in my bucket, I put my hand randomly and I choose. So 2 comes out. So I put 2 here. Okay, I put 2 here and then I put it back in the bucket.
Okay.
And from that bucket, again I randomly choose the second instance, and this time 0 comes out.
Okay.
And this goes on.
Then what is the use of that column? What is the use of that column?
Yes, you are generating more data sets. Now, this data set, what do you think this 2 represents? 2 represents this data set.
ID number. Okay.
This 0 represents this data set. This 2 again represents this data set. So there is repetition. And there is also missing of some data sets. 1 is not there, 3 is not there in this set. Right?
Yes.
Right? So now training on this data and training on this data, do you think will be same? No. So this will generate some output, right? Similarly, you can generate so many combinations of these IDs. This technique is called as bootstrapping, generating multiple data sets from a given data set.
How these are useful in this classification?
Yes. So these are useful because they eventually give you an output which is calculated simplistically with simple decision trees with less number of feature vectors, making it less complex. And those outputs, you could use a majority voting to give a final data. So here you do not need to go through this tough exercise of computing Gini impurities or all these values. And with multiple features, you can have thousands of features and you could still give a very accurate prediction. All you need to do is run iterations. Because it is essentially probability. You need whether it is 0 or 1. It does not matter how impure, how pure it is. What is the majority will essentially decide whether it is 0 or 1. Right? You are concerned with the output. So how about you use the probability, you train it such a way that this entire data set as well as subsets of this data set, including recurrence of data set, is used and the model is trained. Now there is a fit model which can give a very high level of accuracy for your predictions. That's all. Serves your purpose.
No, in making this tree, right, x1 less than or equal to 4.9 tree is there now. To make it, is this a top column is useful?
Yes.
How it is used?
This bootstrapped data has been used and a random feature combination has been selected. And on that basis, yes.
How x0, x1 are selected based on this?
Then select x1, x2. It's random.
Randomly you have to select.
Yes, it's random. So if I compute for 5 such feature vectors, if I have to select 2 combinations, then 5C2, 32 combinations of feature selection are possible for any given data set. So on this data set, I could train on any of the 32 or every of the 32. On this bootstrap data set, I could use a similar principle and select any of the 32 or every of the 32. On this data set again, same. On this again same. On this again same. And there will maybe thousands of such bootstrap data, and I could train on those 32 combinations. So one out of those 32 combinations is this as well.
Mhm.
And I have generated this decision tree. The moment you change this feature combination to x1, x2, or maybe x2, x3, or whatever, the
Tree will
decision tree will
change.
change. And
Will
accordingly, your
change.
output will change.
This column 202455 is the selection of a training data set.
Exactly. From this
Oh,
training data
okay.
set, you are generating more training data sets.
More training data sets. Okay,
Even though
now
you
I
have
got it.
scarcity of your data, say suppose only 6 data points, you
Okay.
can generate a population of so many
So many. Okay,
and
now I
train
got
it
it.
on so many.
Now I got it. Thank you.
Just for the example's sake, on the very first left decision tree, you have taken x1 less than or equals to 4.9. How you got 1 here on the right hand side?
No, one is on the basis of this training data set, which I have
Yeah.
not expanded here. And for features x0 and x1, for example, your value is x1 less than equal to 4.9. Okay,
Yeah.
and your x1 is 6.2. So is this satisfied or not?
Okay. You're comparing this random values. Okay. 2.8, 6.2, 4.3.
Yes.
Okay, ma'am. I got it. Okay. Thank you, ma'am.
Okay, so if that is clear, then maybe we can call it a day. It's
Thank you,
already
ma'am. Thanks a lot.
7:30.